Good day. I am Maranatha Reyes and I will discuss my capstone project entitled Class Imbalance Techniques in Medical Data. To begin, let me give you an overview of our presentation. First, we will define class imbalance. Then we will discuss selected literature on the topic. Then we will discuss different techniques for class imbalance. Next, we will describe the data sets for which we implemented these techniques. Then we will describe our methods, show our results and analysis, and finally give our conclusion. So what is class imbalance? Class imbalance occurs when the examples of one class, usually referred to as the majority class, severely outnumber the examples in the other classes or the minority. Many real-world applications exhibit this imbalance. For example, in finance, banks want to be able to detect credit card fraud. So to make a fraud detector model, a bank would take a database of previous transactions, check whether each transaction was flagged as fraud or not, and use these as labels and train their classifier from this dataset with the aim of predicting whether a future transaction would be fraudulent or not. In the medical field, we want to be able to detect diseases such as cancer. In security, we want to detect anomalies, irregular activities, and the like. However, if we look at the data sets needed in these applications, clearly there is class imbalance. Given the volume of transactions in a day, how many transactions are fraudulent? Maybe 2 to 3 out of 1,000? In a given population, say in a given city, how likely is it that there would be equal cancer patients and non-cancer patients? Out of all activities in a month, say for a particular website, what % of those activities show security breaches? Most likely, not the same number as the normal activities. So what are the challenges with class imbalance? Given that classifiers have more information about the majority, they learn more of it, resulting to bias. Also, the usual accuracy metric that is used to evaluate the predictive performance of a classifier is ineffective for class imbalance datasets. A classic example of this is that if we have a classifier that says all transactions are fraudulent, it would still be 99% accurate, since fraud could be such a rare occurrence. With these interesting applications and challenges, researchers have studied class imbalance techniques, and we highlight a few selected literature on the topic. There have been reviews of methods and applications for class imbalance data by Haishang and Company, Ensemble and Boosting Methods by Galar and Company, and Yan Mao, applications on deep learning by Buddha and Company. There are also 2 foundational texts on imbalance learning. Fatuhi and Company had a review of imbalanced data level methods for various types of cancer. Also, specifically for lung cancer, we refer to Tamimagi's PLCO model for lung cancer risk prediction. These readings have described the ways to address the class imbalance problems that we mentioned earlier. These techniques fall under 3 categories, namely data level methods, algorithm level methods, and hybrid systems. Data level methods involve procedures applied on the training data to make the class distribution more balanced. Algorithm level methods are techniques wherein standard machine learning classifiers are modified and associated with a weight or cost variable, or the classifier itself is unaffected by the skewed distribution of data. Hybrid systems, usually ensembles, are processes which involve a combination of sampling techniques and algorithmic methods. In this project, we implemented data level methods and hybrid systems. Data level methods can be categorized into undersampling, oversampling, and hybrid. Undersampling involves reducing the number of majority samples. Oversampling entails increasing the number of minority samples, while hybrid combines the best of both worlds, undersamples the majority and oversamples the minority, all of these to achieve class balance. For this study, we implemented these 10 undersampling methods. The most basic undersampling method is random undersampling, or RUS. and it takes away random examples from the majority until the balance is reached. However, this could lead to throwing away important information, so researchers found many other ways of choosing which samples to discard from the majority class. And here are the other undersampling methods. We also implemented 6 oversampling methods. Among them, the simplest one is random oversampling or ROS. It picks a random minority sample to duplicate and repeats this process until minority samples reach the same number as majority samples. However, this could lead to overfitting because the classifier could be memorizing the same samples. So again, researchers found other ways to expand the minority samples in the training set. Among these, SMOTE is a popular oversampling method. It produces synthetic examples by interpolation. It has been extended by others, thus we have SMOTE nominal continuous, borderline SMOTE, SVM SMOTE. For hybrid methods, we implemented 2 techniques. The first one combines SMOTE for oversampling and edited nearest neighbors for undersampling. And the other combines SMOTE with atomic links. For ensembles, we implemented these 4 methods. For the data level methods, after oversampling, we use these well-known classifiers, namely logistic regression, random forest, and linear SBC. As we are interested in the application of these techniques to medical data, we utilize 2 datasets, namely the PLCO and the NLST datasets. For PLCO, we focused on the lung dataset only. With these datasets, given clinical data, we aim to predict the presence of lung cancer in an individual. In this graph, we plot the number of lung cancer versus no lung cancer samples for both datasets, and we can clearly see the class imbalance. In particular, only around 3.9% of the samples belong to the minority class, both for PLCO and NLST. The variables that we have used in our models consist of a mixture of numerical and categorical data. For numerical features, we have age, number of years since quitting smoking, number of years smoking, and pack years to include the intensity of smoking. For categorical features, we have body mass index category, history of bronchitis, smoking status, that is if the person is a current or former smoker, educational attainment, history of emphysema, family history of lung cancer, and X-ray history, for a total of 11 variables. Next, we describe our methods. For pre-processing, we cleaned our data. For the missing values, we either removed them or used scikit-learn's imputer. An example of those that we removed were PLCO examples with no smoking status, which also had missing values for other variables such as number of years smoking. Also, we had to align the PLCO and the NLST datasets. We used a stratified 10-fold cross-validation to ensure that we have consistent class imbalance ratio in our training and test sets. For our numerical features, we performed min-max scaling to reduce the values in a range of 0 to 1 using the given formula. For the categorical variables, we used one-hot encoding. For the data level methods, we performed sampling first, then we proceeded to train the model. Next, we validate our model by pre-processing the test set, predicting, and then finally evaluating the performance metric. We use the AUC or the area under the ROC curve as this is the more common metric used for class imbalance. Now, here are our results. For the undersampling methods for the PLCO dataset, each classifier had its own best undersampling method. For logistic regression and linear SBC, the best performers are not too far from one another. For oversampling methods, random oversampling performs well with logistic regression and linear SBC, while SVM SMOTE performs well with random forest. In hybrid methods, SMOTE-E and N obtained higher AUCs in all three classifiers than SMOTE-TOMEC, but it is not too far behind. For ensemble methods, Easy Ensemble got the highest AUC among the four methods. In summary, these are our findings for the PLCO dataset. We also apply these techniques to the NLST dataset, and here are our results. For undersampling methods, each classifier had its own best undersampling method. For logistic regression and linear SVC, the best performers are not too far from one another. For oversampling methods, random oversampling performs well with logistic regression and linear SVC, while SVM's mode performs well with random forest. Notice that these are the same methods that performed well in the oversampling portion of the PLCO dataset. In hybrid methods, SMOTE-E and N obtain higher AUCs in all three classifiers than SMOTE-TOMEC, but the difference is small. For ensemble methods, Easy Ensemble got the highest AUC. We summarize the results for NLST as follows. Next, we compare the best performing sampling methods against classifier baseline, meaning no sampling for both datasets. We can see that compared to the baseline, applying the appropriate sampling method can increase the AUC of the classifier. Overall, the method's Easy Ensemble classifier was the top performing model for the PLCO dataset. For NLST, it was the top among hybrid systems, but was a few points behind the top performing model. To gauge the overall performance of the Easy Ensemble classifier, we trained it on the full PLCO dataset and then tested it on the NLST dataset, achieving 61% mean AUC. In conclusion, class imbalance techniques can help improve the performance of a model. In particular, we have shown that well-performing sampling methods of each classifier had higher AUCs compared with the baseline classifier, and that the Easy Ensemble classifier, which is a hybrid system, had the highest AUC in these techniques for the PLCO dataset. We have also seen that generally, NLST obtained lower AUCs compared to PLCO, indicating inherent differences in the data. That concludes our presentation. Here are our selected reference materials. And thank you for watching.